Many pilots today don't go out with an immediate concern on their flight that they're going to run into the ground.
There is a problem in aviation of controlled flight into terrain.
Controlled flight into terrain is a case where you have a perfectly healthy aircraft that is what's called under controlled flight. In other words, it hasn't stalled. The pilot has full control ability of that aircraft. Yet, the aircraft ends up running into the ground in some way.
We're developing an automatic system to avoid a ground collision in the case of a fully functional aircraft,
which will automatically take control of the aircraft and automatically fly that aircraft away from the ground to save the pilot and the vehicle.
You don't need a multi-million-dollar fighter with digital fly-by-wire flight controls and very expensive hardware to implement a system like this.
We can put these algorithms that determine if there's an imminent ground collision. We can put them on a phone, which we've demonstrated with the Droid, and give out that application.
When you go from an F-16 to something like a small UAV, we unplug the F-16 model, we plug in the small UAV model, and the rest of the system remains fairly much the same.
The technology that we're developing is important. We all have friends and colleagues who aren't with us anymore because they've run into the ground.
In the fighter area, there were about 1 or 2 people dying a year in the Air Force alone due to this controlled flight into terrain problem.
And that is when an airplane in perfectly good health crashes into the ground due to either pilot error or possibly the pilot is unconscious. As in fighter jets pulling high G, they may lose consciousness.
This is something that is not just confined to military aircraft, and it's not confined to UAVs. General aviation aircraft have a big problem with running to the ground. Pilots do for whatever reason. They're distracted, they can't see, they're in a fog bank.
Another case is where they are spatially disoriented. A good example of this is the JFK Jr. mishap that happened out on the East Coast a number of years ago.
They fly in sometimes extreme landing and takeoff locations up on mountains and things where their aircrafts don't have the aerodynamic ability to climb like they think it should.
A number of years ago, the Defense Safety Oversight Council, out of the Undersecretary of Defense for Personnel and Readiness, saw this problem and asked us to begin addressing it for fighters. In conjunction with the Air Force Research Lab, and Lockheed, we went out and did an initial program on the F-16 that would help address the problem on all Air Force fighters.
The ground collision avoidance maneuver chosen for the F-16 is a wings level climb. It climbs really well and it doesn't turn very well, so we don't try to turn in front of an obstacle, we try to climb up over the top of the obstacle. So regardless of what position you are in the F-16, if there's an impending collision, the airplane will roll to wings level and begin a 5 to 6 G wings level pull to clear the local terrain.
Okay, you're going to roll inverted, pull the nose down. It's going to roll itself upright and pull. Bingo. That's all automatic.
When you have that kind of automatic computer actuation of a decision, and you have to take into consideration a few more things than a warning system would. Don't make things worse is the first requirement. The second one is don't get in the way of normal piloting activities. And then the third is actually avoid collisions.
You got an autopilot that has the ability to really move this airplane around. We have the ability to put 6 Gs on this airplane. 6 Gs is not an easy thing to withstand. Fighter pilots get used to it, but still 6 Gs when you didn't ask for it is a surprise, and it's really going to get somebody upset if it didn't have to happen.
Pull up, pull up, pull
It's
up,
just downright
pull
annoying.
up. Altitude.
What ends up happening is, after a few false warnings in the cockpit, a pilot either tunes out the warnings or turns the system off, and now that warning system provides no benefit.
In a fighter airplane, these collision avoidance maneuvers are very aggressive. So when they happen when they shouldn't, it's going to get away of the mission and it's going to upset the pilot severely. So avoiding nuisances in a fighter airplane is extremely important.
Their concern was that they weren't going to be able to carry out their mission and that the system was going to interfere. When they were shown that they could still do their mission and the system would actually wait longer than they would before initiating a recovery, they realized that this is not going to be a problem.
We believe that the system we developed in the ACAP program that's being fielded in the F-16 now will prevent above 90%, maybe as much as 98% of the mishaps.
We went out and tested the system against every historical category of controlled flight in terrain mishap that the F-16 has seen and based them on actual mishap cases. And we showed that across the envelope of operation of the system, it prevented every single mishap. We wanted to set up a system that would be easy to adapt to any different aircraft. At the heart of that is a modular software architecture.
And these pieces could be replaced, like an F-16 piece could be removed from the system and then a UAV piece inserted in, and then the rest of the algorithms could remain the same.
The F-16 represents the high performance top end of the performance spectrum. Airplanes that go real fast, climb real well, have great climb performance, but because they're going fast, their lateral turn performance is not as good.
In the case of a small UAV aircraft, like the Droid, we have a limited climb performance, something very typical of a general aviation aircraft. That performance model is very different.
And hopefully by anchoring both ends of that spectrum, we cover everything in between.
I think it makes it a lot more plausible that we could move to a different aircraft all across the spectrum of aviation.
One of the main costs in bringing any kind of a capability to an aircraft is the actual hardware.
A very small difference in where the airplane actually goes.
We had an eye in the future, and we recognized that eventually we wanted to get this into the general aviation community. And the best way to get something into the general aviation community would be to put something on tools that would be readily accessible to them.
So we moved the software from high-dollar fighter hardware processors to cell phone. And we've now migrated it onto a cell phone app.
At bare minimum, an app that would warn you. The more advanced versions would tie into an autopilot and actually take control and recover the aircraft. Not all general aviation airplanes have the autopilot that would be necessary, but at the bare minimum, it's an app that you can put on your cell phone and you would get a warning that you're about to run into something.
And that has enabled this technology to be potentially brought to the rest of the public for a much broader application and life savings.
I couldn't tell on that very first run.
The basic pieces that are needed to make this system work are an understanding of where the aircraft is. This is provided through GPS. You also need to know what the terrain is around you. So we have a computer model of the world that is a digital database of elevations. We then, inside the software, have a model of how well the aircraft can perform. And that model is very precisely tuned to that aircraft's performance capability.
Even since they first started developing this capability back in the 90s, capabilities of computers have gotten much, much better. The capabilities of GPS navigation systems have become better. The terrain database that allows the aircraft to know where the ground is, where the mountains and the valleys are, has gotten a lot better.
What we did was, how we kind of overcame that is we had to go to different sources, and we kind of have this mishmash of sources that are at different resolutions and different accuracies, and we put those together into our, a custom database that really I think is tailored more to what we're doing with AutoGCAS than the original databases were.
We have built a utility that compresses this terrain into a rather small file size such that we can carry the entire globe on the phone.
So we got a homogeneous, much more accurate digital terrain database to use now. So by using improved digital terrain, we get improved performance, and then by using an improved navigation system, we know where we are over that terrain much better. So we can predict the airplane to terrain collision geometry much better than we could 10 years ago.
The system monitors the approach of the ground and the aircraft's ability to maneuver to avoid it.
It predicts an escape trajectory that keeps the aircraft on a forward trajectory but pulls it up away from the ground. But it also computes a trajectory that moves the aircraft to the right and one that moves the aircraft to the left.
It compares these two things, the terrain and the aircraft's ability to avoid it.
If the system thinks that the aircraft is in trouble, it will select the last possible option of those three trajectories.
It isn't forced to try and climb over it. It can turn to the side of it. That's unique to the droid system that we've developed, and that is a feature that will likely have a great advantage when we take it and apply it to general aviation aircraft. On a typical day of flight, the team shows up here, and early in the morning we gather all our gear, we load it into our command and control van, head out into the field, assemble the aircraft, set up our systems, and then go through a series of tests.
Our first flight's going to be against that hill, pilot flown through the gap, and we're using 2 VHF frequencies for...
What I've been doing is operating our user interface, which is the link really between us on the ground, the test team, and the phone.
When we do a run, we actually set up the autopilot through the ground and control station. We give it a point that it's going to fly to that's actually under the ground. We're telling it to, really run into the ground. The system is monitoring this, and at the last instant disengages that autopilot system and uses the auto collision avoidance system to take control of the aircraft and avoid hitting the ground.
1, 0, fire. Upright. Run complete. Yes, control.
Just over the course of our testing, and we went through our testing as rapidly as we could, there were no fewer than 5 fatalities and 7 mishaps that we could have prevented with that software on the very fighter aircraft that we were trying to design it for.
I think the system we're fielding now with the F-16 isn't perfect, but I think everybody in the field is going to love it, and I think it'll save lives.
Do we have the perfect answer? Of course we don't have the perfect answer, and that's something that's going to evolve over time.
But we're trying to save lives. We're trying to save pilots and passengers' lives from controlled flight and terrain.
NASA's taking the risk, and the Air Force is taking the risk to put the system on, and I think, I really do, that it'll be game-changing and save a lot of lives and really be a benefit to society and really show what's possible.
I think it's a system whose time has come. There's no major obstacles from a technology standpoint. It does take work, it does take development effort, it takes flight tests to prove it.
The technology is out there to do this. It's a matter of bringing all the pieces together and sewing it together with software to make the capability happen.